done one of these in a long time, so I'm rusty. This is a kind of a thrown together talk, and I'll also issue a caveat or a warning. I'm not going to tell you how to do anything. Basically, I'm going to show you how to wander around in various things. But the title and the talk is true to form. I really do want to talk about communications theory as applied to anything that you'd like under the sun. So, I have this, Paul, like I said, you were the first physicist that I met that I liked. But, in my generation, which is kind of, it's interesting. I guess now I have a few gray hairs. I can give these sorts of talks. But in my generation, Sputnik, I was a baby when Sputnik was launched. And or maybe I wasn't even born, now that I think about it. But it was in that era, so there was the space race and the Cold War. Physicists reigned supreme. Physicists were the scientists to be. And, if you think of a physicist, that's who they are. They're the power, the superhero, they're the wonder. Look, they have a few minor successes. There's quantum theory, there's relativity, there's atom bombs. So, they have a few things that they can brag about, but, come on. So, in contrast, my chosen avocation, when I did my undergraduate degree, I had a choice between physics and electrical engineering. And I came from a working class background, so the idea of thinking about quarks, things like that, where nobody would actually pay you, worried me a little bit. So I became a double E. And then I kind of drifted into, I did some biophysics, so I kind of tried to keep on doing physics, but then I drifted into communications theory, which was kind of cool. It was a way of looking at the world. And the thing is, if you think about communications theorists, how they might be viewed, there you have it. And that's so tremendously unfair, right? I mean, it's we invented the internet. Shannon, communications theory, all the things that communications theorists have done and can lay claim to, and will lay claim to. So that's really not that that's a kind of unfair. But such is life. Life is unfair. But then I got to thinking about it in marrying, my old age now, marrying these two interests, kind of circling back around to what I used to know, what I used to do. If you think about communications theory, it's everywhere, right? How does another atom know that there's another atom nearby or not nearby? How do things interact? They exchange something. There's physical laws, but they exchange something. Simple things, bring it to a little bit more macro. If that wall were really, really hot, raging fire behind that wall, you'd know it. Because there's information being transferred from that wall, the molecules of air in the room, to you. So there is messaging going on, but it's not couched in the engineering way that we couch communications. So, you can keep on going on. I have a whole long list here, birds and the bees, just for the heck of it. That was poetry with cells, organisms, and ecologies. Economies and societies, and the universe. Everything communicates with each other. Stuff knows that stuff is there. So, how do you begin to quantify that? So, my mantra for as long as I'm technically active, or as long as this works, even it may turn out that communications theory is a stupid way to look at the rest of the world. I don't think so, but might be. I think the way I like to think of it is, what are all these things talking about? And how can we look at them? How can we interact with them? How can we actually extract information? So, that's all up there. I'm going to talk about specifically 4 different things. One of them, you guys know really well. And the funny thing is that this example, what I'm going to talk about, may be completely useless for my own channels. But it's where it got me thinking about physical interaction and how to think about communications theory in different ways than communication theorists usually think about it. So that's the first thing that I'll talk about. I'll try to be relatively brief. I've got an hour. I've got 40-odd slides, but they should be fast slides. Watch my time. Then I'm going to suggest, after we look at this MIMO system, the thing that's going to occur to us, kind of obviously, is that physical things, macroscopic physical things interact. And this particular picture, you've seen this. Anybody that's taken a physics course, so everybody in this room who has not taken a physics course, raise your hand and then leave. Okay? At some point you've taken a physics course. You've seen this system or a version of this system. Turns out, if you get rid of the ground plane, you need a reference, you know, sliding and the friction and all like that. You get rid of that stuff. Crystal lattices are modeled that way, or can be modeled that way. The other thing is that the things that describe this system can be macroscopic, but you can keep on drilling down till eventually you end up with a discrete description. So I want you to keep that in mind. How many of you know what that is? Who does not know what that is? Okay, so everybody else has taken biology and seen these things. That's one of our favorite little beasts. If you buy fruit, you end up with fruit flies. That's Drosophila. You're saying, where's the fly? Well, you know, it starts out as a bunch of cells, and it develops into something else. Those cells are talking to each other. There's no question about it. Those cells are talking to each other, and they're somehow constructing this marvelously complex thing, like us, by talking to each other, these individual similarly programmed units. Now, I'll take a quick side jog. I got interested in the biological problem when I met a physicist slash biologist from Lawrence Berkeley Labs. And she was working with a woman who studies breast cancer. And Nina Bissell, what she found with breast cancer is that cells can be genotypically prone to breast cancer, meaning they want to become cancer. In their genes, they're going to become cancer. You take those cells, you plate them out in culture, they get malignant. They go crazy. However, if you coax them, these same cells, if you coax them into a structure that looks like, I want to call it an alveolus, a sinus it's called, in just like a little pouch where the milk collects. But if you coax them into this kind of structure that has a duct and a sac, suddenly they chill out. Okay? No other things apply, just the structure. So, you know, a communications theorist looks at that and says, who's telling these cells what to do? You break them out of that same structure, they become malignant again. So somehow structure is communicated from these cells to each other, which is a weird sort of thing. I'm not really going to talk about that in particular today, but that's what got me started. And then the last question is something that another buddy of mine, who was a patron saint when I was coming through school for actually a generation of students. He was the physicist's physicist. And he's come upon this new way of looking at the world. And you know, we've all read about this stuff in the New York Times about super-symmetry. You know, everybody knows, you know, string theory, vibrating strings, particles, things like that. Here's the amazing thing that freaked me out about this. It turns out that all of us who do communications theory we have the same mathematical tools, or much of the same mathematical tools that these particle physicists have. And I'll explain that, you know, as we go on. And it so happens that these new structures, which are represented by this graph, it turns out that they have a communications theory construct embedded in them, which is kind of weird, and we don't know why. And I'm just, you know, tagging along at this point, and waiting to see if there's something really deep and interesting. So I'm going to talk basically from macro down to micro, down to sub-micro, and just give you a flavor of things. So what I'm going to try to do here, and by the way, you know, you're allowed to interrupt because I can skip and go in quick between. But the basic idea is that energy is one of the things that we deal with as communications theorists all the time. We either deal with it, or we're either trying to preserve it, we're trying to get information across under some sort of energy budget. That's what we do as communication theorists. So that's always there. And physics is just the same. Energy is at the center of physics. This is the thing that's kind of cool. If you look at things, you can think of things as discrete fabrics. Okay? So that's what the digital age has taught us. We can look at things as digital. And what physics has shown us, and what Jim in particular, or my buddy down at UMD, is beginning to think, is that there really is. Wheeler, who I don't know and barely know claims to fame, has always talked about it from bit. So the idea that the universe is somehow specified digitally. It may be. So you have all of these things where we sit as communications theorists, coupled to energy. So it seems like some of the things that we do, this, by the way, physicists who really understands information theory. Okay, sorry, Paul. But what they usually understand is, I know entropy, so yes, I understand information theory. No, you don't. Okay, and the hard thing about information theory is the inequalities. And we're, some of us are better than others. I'm not really good at that, but that's what the information theory is about. And maybe that stuff can supply us some conservation laws. Basically getting our arms around the system so that we can understand what things can do, what things can't do, and when we should be surprised. So with this sinus, with the breast tissue, should we be surprised that these things can talk to each other on a time scale that allows them not to become cancerous, or not? So those are the sorts of questions. So I'm not going to answer and say, this is the way to look at any particular problem. This is kind of a overview. So having said that, there's my disclaimer, okay? And here's what I just said. We're just going to walk along a few garden paths. I mean, I guess, I should think basically like me, because if I were in the back, I could barely see it here. My eyes are so old. But just a stroll along garden and if you don't see something, scream at me and I'll tell you what it is. Okay, so here's this mindless system that you saw before. And I'm going to ask you to suspend disbelief right now, because you need to suspend disbelief. Basically, do we need to know the channel perfectly everywhere? It's been a lot of work done on what you need to know where, what helps, and what doesn't. I'm going to ignore that for right now.
Chris, what's CSI?
I'm sorry, channel state information. Thank you. All right, so everybody's seen this, right? Well, excuse me. How many people do networks? Oh, see now when Roy raised his hands. Okay. How many people do
so is that laugh?
communication physics, like spread, signal space, that sort of stuff? So everybody works at a higher layer these days. I know you guys. All right, but so you've probably seen this. Certainly, if you've taken if you do a communications theory, you've seen something that looks like this. We have a received signal, information you're trying to send, symbols, and some multiplying factor, which is a gain matrix. So these are all vectors. That's a matrix. There you go. So the question that I began to wonder about, because it's almost dogma, right, is that if you look over the past, Jerry, when did you? I know I'm going to embarrass you, but when did you and Mike invent MIMO?
It's like 94, 95. Something.
All right, so 15 years, right? Over the past 15 years, not too much has changed in terms of the actual channel model, at least to my knowledge. But the basic idea is this. If you're sitting in an environment where there's stuff moving around, radio is notoriously flaky. We all know that. The channel changes, it varies, it's a function of time, space, everything. So what do we do as communication theorists? We kind of throw up our hands, right? We say, can't know it. So then we get a statistical description, and we build around that. It turns out that that's been outrageously successful, building around that statistical description. But my question is a little bit different. I'm loath to just jump to statistics when maybe I don't have to. So the question that I ask here, and I want you to follow along with me, again, suspending disbelief, is how well can you know a MIMO channel? Okay? Could you know it really easily? So let's just do some thought experiments. Some of them are right, some of them are wrong, or fudges to some extent, but here you go. So I've got an n by n system. I've got n antennas over here, n antennas over there, or maybe it's the other way around, doesn't really matter. It's some n by n. There's some number, everything's with DSP these days, so there's a k-bit specification in the channel games. There's some number of seconds between when you think the channel is stable and when it's changed, so that's tau. And, let's just do a quick calculation. So that's my number for the data rate to specify the channel. There's k-bits per entry, there's nm entries, and it's per unit per that unit time. And if you throw a few numbers here, k equal 10 bits, by the way, so I have somebody that can actually answer the question. When people do these gain matrices and actually do the DSP, how many bits do they code the gain matrices with? Anybody know? I mean, I'm kind of looking at Jerry, but I don't want to put him too much on the spot.
I think it depends where you are with the capacity.
Right.
The more refined you have to know it, the higher the capacity is.
Okay.
The radios typically have 16-bit resolution, but you're only operating with maybe 12 bits of it.
Gotcha. Okay, so I'm in the ballpark. That's the point. Same. Tau, I haven't even talked about Computer's time. First off, because I don't really believe in this time. Is Larry here to yell at me? Good. No, he's, Larry, if you're out there, you can call in and yell. So megabit per second per user. Okay, a megabit per second per user. Not too terrible. All right, well, let's look at the underlying channels. Why people think about these channels as completely unspecifiable and unknowable. All right, so we'll pick a 3 gigahertz multipath channel. I picked 3 gigahertz because the wavelengths are easy. Scatterers, I'm going to put them in a football field, 100 by 100 meters. So they're things that radio bounces off of, and they're in a football field. Positional accuracy, roughly, let's say 1/100th of a wavelength. That may be too much, but it may be too little, but that's not really going to matter that much. So, you put all these things together, and you end up with, if you have 1,000 scatterers, you need 34 kilobits to specify their positions so that you can calculate the channel gain matrix. Okay? So that's not a lot. If I have more, it's, say 1 million scatterers that are significant, I have no idea of the physics of the scattering, whether that's significant or not. But, that would go up by a factor of 1,000, and it's still not ridiculous to think about.
How do you get 17 bits per scatter?
Oh, okay. Specification to wavelength is a centimeter. Okay, specification to a millimeter, or I think it's not centimeter, 10 centimeters, right? For 3 gig. Right. So specification to a millimeter, and if I need to know a millimeter in a 100 by 100 plane, I just chop it up digitally.
Yeah.
And I'm assuming uniform.
And one more thing, because the original positional accuracy was 1 millimeter. That was, right, you want to specify to a millimeter.
Right.
Then down below, you want to make it 10 microns, 100th of a millimeter.
Factor of 100, 10 more bits, not even 6, 7 more bits. So it's not going to go up by a lot. Are we okay or not?
Just a little bit.
You don't like the 48?
It should be a factor of 100 cubed, or a million.
Oh, are you talking about 3?
Yeah, the volume.
Okay. So,
Am I wrong?
No, you're not wrong. You're not wrong. I just did 2.
Fine.
Okay, but that's all right. Take 3, okay?
Yeah,
you want a tesseract? I'll give you 40. Okay? You see where I'm going, right? It's just you add, okay, and then you multiply by the number of scatterers.
Yeah.
Good. All right. So, the point is, it doesn't take that much to specify the channel that way with individual scattering elements. All right. Well, now life gets more interesting. If they were all in one place, right, then it would be really easy. All you have to do is log your motion and calculate the channel. I'm being silly. But scatterers are moving, and I'm really being completely, off the cuff here. I'm not talking about a lot of stuff, but they're moving at 10 meters a second, say, which is not that fast, but not that slow. If it's a millisecond update, meaning that it's if you move and move a half of what is it? This might have been 20 before, I don't remember. But in this order of magnitude, position changes per second, meaning you're moving these deltas. So if I move from 1 millimeter to 2 millimeters, that's a change. 1,000 scatterers, 10 micron specification, channel specification rate. Well, it's now 10 to the 9th bits per second. That's getting where wireless people were getting kind of uncomfortable about that. A gigabit over a wireless channel is a fair amount. Yes, sir.
The changes in these channels are actually because of tiny changes in phase, right? And so
Where things bounce.
at 3 gigahertz, it doesn't really matter if you're moving at 10 meters per second or 1 meters per second. It'll still be about the same number of bits you need to specify the channel per second.
I'm asking, I guess what I'm setting up a straw man for a reason. What I'm saying is that if I move a millimeter, I'm going to say that I have a new channel. Okay? That's not necessarily true, okay? But I'm going to set it up that way. Okay?
I guess an alternate setting, and this is where people will bring in correlation distances and so on, is you have a huge cylinder, and waves are imploding randomly off the surface of that cylinder. And you're moving, and you have this array that you're moving down somewhere around the center of that cylinder. And now you can, from the independent phase implosion, you have IID random variables, you get a Gaussian process, you get a correlated Gaussian process. And what am I talking about? You have one antenna, this would be the Jenks process.
Yep.
And so that would be a model, an alternate model than yours.
Completely agreed. Completely agreed.
And you have correlation in that Gaussian process, and it'd be a vector process, and ultimately a matrix process. That'd be another way to look at
No,
it.
completely agreed. But again, what I'm going to ask you is to just bear with me just a bit, because I'm being a little flippant, but I think I have a point, and then we'll see if I have a point later. So, I'm saying that that's large, and I'm going to say at the bottom, ooh, it's large. All right. Now, here's where the physics comes in. What's actually moving out there? Okay, cars, trucks, automobiles. Okay, you mentioned things moving, about a wavelength. Well, how much does the Empire State Building move? Okay, I'm not asking, kind of, but the point is, it moves. Okay, and it moves in a significant sort of way relative to a wavelength. And if it didn't, it would fall down and break over that region. Right? So things move, right? How do things move? You got to push them. And if you got to push them, that means you got to apply energy to them. So that was the germ of a thought. So what I did was I said, all right, there's some sort of mobility process on the scatterers out there, including the thing that's moving. This is an abstraction. There's some channel physics. If you know where stuff is, you know the channel. So that's a function. There's no stochastic process, no stochastic nothing going on in here. There's the stochastics, there's non-stochastics. Sorry. Stochastic, stochastic, non-stochastic. All right. What are you going to do if you want to measure this thing? Well, shut off your data stream, send in probes, and you're going to get responses. Right? There's kind of an inversion of the problem, usually, right? Because usually this is the information, and that's the thing that's transmitting the information here. You're designing probes to send the information that is G. Okay? All right, so you set that up, you do some stupid information theory, which is not that, brilliant. The maximum rate at which you can extract information about the channel is this number. Okay, say, so I'm going to define that as R. I set that up, we don't care about that. So here, if there's a static channel out there, and you want to get information about it, and you have n times to probe the channel, roughly, I'm being very quick and dirty here. If the extraction rate that you can pull is greater than the information rate, the entropy rate of that channel, then potentially you could learn that channel. It's certainly the case, though, if this rate is lower than that entropy rate, you're screwed. Then that per probe entropy, you're screwed. You can't. It's just a statement of the source coding here in the channel. Yeah. All right. Then there's this issue about tracking, and this is where it got really interesting for me in an intellectual sort of way. Here's the rate that you can extract information about the channel. Here's the actual entropy rate of that process. Okay? All right, I'm going to stop quick there, and I want to point at Roy. Since, we've talked information theory together, and now he's the Johnny on the pony, and I'm going to try to usurp him. I need to learn the stuff he already knows. So,
Hopefully I won't say anything stupid.
oh, you won't. Oh, no. If you say something stupid here, I'll know that you had a bad breakfast. All right, so here's the question. All right, there's nothing stochastic in there. Here's a random process. Here's another random process. What can I say about the entropies of G and X?
Oh,
Give them
somehow
those-
your entropy of G has to be less.
Right, less that can only be as big as. Wasn't that brilliant? Okay. And he'll even cite the theorem for you, data processing. So there it is, data processing, that's true. And this little squiggly H, everybody, who has not taken information? Don't even. Didn't you ever take an information theory course, Paul?
No.
Come on, Paul. Get with it. Oh, well, who am I asking, Jerry? All right. That squiggle means entropy rate as opposed to entropy. And in this particular case, it would be a differential entropy rate, blah, 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 blah. All right. Now, here's where it got interesting for me. Here's a question. I have this thing here.
Chris, can you just give me just an intuition? Just
Right.
an intuition. Not a challenge. You had that box with the process. You had random in, random out, and a box. There you go. And I would have thought, obviously, this is pure ignorance, that if the channel physics
By the way,
was
just a
something,
second. Anytime we're from an old culture, now I'm on guard. Okay, so go ahead.
but if the channel physics was something like a reversible process, that's the only way I can think about these things,
Yeah.
then the entropy associated with X is the same as the entropy associated with G.
Depends. Here's why. No, I'll tell you why. That's actually a lovely question.
But let me add one more, and then you give the answer. And if the channel physics is not what I would call a reversible process, then the entropy on G has to be bigger. So I'm completely
Careful. If I give you positions, can you specify the channel?
Yes,
Okay, so that's a function,
yes.
right? So the point is this, unless that function maps to, if it maps to exactly the same, if it's invertible,
Yep,
then just like you said, the entropy of that is going to be the entropy of that,
Right.
no question. If it compresses down, meaning that there's some sort of overlap, for different x's we get the same g, that's it. And did I answer your question? There's no
There's no
randomness introduced in this
process,
mapping.
there's no one,
There's no process in that channel physics. It's just a functional map.
it's just a function.
Yeah, there's nothing, there's no hidden randomness pumping up through here. And that's
So in
why,
that case, the entropy in G is smaller.
yes, less than or equal.
Fine, thank you, sir.
Data processing theorem, that's why. Are you teaching it this year?
No,
Too bad.
taught it last year.
You missed it. All right, data processing. Let me quick zip through this. Here's my question. I have this thing here. It weighs, I don't know what the hell it weighs. I want to get it from here to there and stop it by some time tau. Well, how much energy does that take? Turns out you can solve that variational problem, and anybody that grew up when I grew up knows the answer. You don't hear about people firing their retro rockets like for an hour, right? You fire your retro rockets when you're out in space, like that. You bang them, and then you move on. Turns out that the minimum amount of energy is basically a little impulsive sort of thing. You apply the energy to the thing, move it there and stop it. And that's the best you can do in terms of energy. So I'm going to use that as a lower bound. Okay? So you got move mass m by distance d. Now, you have an energy budget, right? If I want to move this from here to there by a certain time, and that time is a nanosecond, okay, so it's about a foot. Okay? I just kind of shot myself in the leg there, right? So from there to there in 100 nanoseconds, right? I got to use a lot of energy to get it from there to there. Okay? I'm not going to talk relativistic sort of stuff here, so from there to there. So the point is, the faster you move stuff, the more energy you got to have. So there's a relationship here about uncertainty. So for example, I always tell my students when I talk about stochastic processes, about midway in the term when they're beginning to not know whether they like me or not, I'm in front of the class and I say, well, my position is a random process. And what's the probability that I'm over there a millisecond from now? And they secretly say, we hope it's 1. Right? Because that implies a whole lot of energy that had to be applied to me. And that would be disruptive. So here's the question. You can now figure out, if you have a certain energy budget, what's the most random you can be under that energy budget in a given time. So this is the maximization that you've all seen at some point, or a version of which you've all seen at some point or another. We're going to find a probability distribution on position such that we satisfy some sort of energy constraint. Energy constraint is a mean square constraint. Blah 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 blah. Surprise, Gaussian. Except that it's discrete, so it's Gaussian-ish. And you do a bunch of stuff, you end up with these expressions which I'm going to ignore. So let's do it. Let's do our position updates at 1 millisecond. Just making that up. We'll do it at 1 millisecond. Energy budget, I'm going to say it's 1 joule within that millisecond. Okay? And any of you that have been on an exercise machine know that a joule per second is a kilowatt, and I can't keep up that rate of expenditure myself. I'm sure Olympic athletes can, or semi-Olympic athletes, or Roy can.
No athletes.
Okay, so
Like the greatest bicycle racers are all around 800 watts, not a kilowatt.
so we're being
Or maybe like for 50 yards at the finish of
Right,
those
like a
sprint
burst.
finishes, they go like 2,000 watts for maybe 5 or 10 seconds.
2,000 watts. All right, so I'm not going to make some stuff up, and I'm glad you're at the top. You can sing your praises again. So, let m equal 100 kilograms, that's 220 pounds, not anymore. So that was 4 years ago. We've got this epsilon. You do the bunch of calculations that I showed on the previous page to calculate out what the entropy is, and you end up with 0.09 bits per dimension. Okay? And 0.9 bits per dimension. Update time is a millisecond, so that's 90 bits per second per scatterer per dimension. If 1,000 scatterers, 90 kilobits per second. Seems paltry, doesn't it? Not that large. And make it larger, it's 90 megabits. It's 1,000,000 scatterers, which I have trouble buying, but let's go there. By the way, if you drop the mass down to 1 kilogram and apply a kilowatt to it, I'm trying to think of a physical system where you're taking a kilogram and you're applying a kilowatt to it. 1 joule, right, is like raising a kilogram a meter, or accelerating a kilogram to square root 2. Yeah, square root 2 meters per second. Okay. So, that's a fair amount of jiggling you'd have to do. So most likely, for smaller things, that energy budget goes way down. But even if you kept it, this pops up by a factor of 20 to 2 bits per dimension. Okay? Yes, sir.
Why are we thinking of humans moving objects? Why not things like cars that have much more energy?
Great, that's fine. But even there, okay, now the car is now a factor of at least 10, right? More like 20 of this. So the mass goes up. And then you think about the energy. And here's the other thing. A car moving along a straight line. Let me get to that. Well, I can get to that right here. Wrong. I don't have it. It was here, it's gone. A car moving in a straight line, how random is that motion? Not very. What I'm talking about here is maximum randomness. I'm taking that car and I'm moving it, okay, with the car's engine. So that's hard to do is the point. So I'm trying to be worst case. I'm also spending a whole lot more time on this, but soon I get it probably useless. In any case, the point is that when you look at these numbers, it doesn't look that ridiculous to actually know the channel, perhaps, if you use the underlying energy considerations of the stuff that's moving around. So that's the main point here.
Like saying you want to know the channel, what physical quantity do you want to?
I want to know the gain matrix. So if I know the position of the scatterers, the implicit, not saying it's easy, implicitly, once I know the scatterers and I know my position, I can calculate the gain matrix. Wink, wink, Mike Ann's lab survey. Okay. In any case, I don't know whether this is practical. Probably isn't. And it certainly could be useless, because one of the nice things about MIMO is that you're averaging over channels. Right? But there it is. This was the punchline. But what you thought was unknowable, you said, oh, stochastic. It might not be. It might be knowable. And that forces us to dig a little bit deeper in physical systems as energy constraint information flows. So that brings us to the next slide. Here's our system. Sorry.
So basically you are saying that you are taking out the stochastic nature of the problem and
No, what I'm doing is I'm bounding how stochastic something can be based on energy, which is a pretty typical thing. How do I know what the temperature of a gas is, right? That's a measure of randomness. Measure of randomness is the energy. Was I making sense, basically? So here's my spring, whatever. I'm going to blaze through this stuff. Here's the equations of motion. You've seen these all before, in one shape, form, or another. Those are state equations. We solve the state equations. Here's the interesting thing about it, though. And this was what kind of fascinated me about it, because I've taught linear systems courses, I've taught communications courses, I've never really kind of brought them together. So there's the output. The output in this particular conditioned system is the position of that last mass. And here's the equations of motion. But here's the interesting thing. See that phi? Okay. That comes from this matrix A. And for a given size A, there's exactly n by n A, there's exactly n of those functions. And so for communications theorists, what does that immediately make you think? N functions. Oh my goodness, let's build an orthonormal basis and project everything onto that orthonormal basis. So once again, not an approximation. I can now completely specify this output, the homogeneous case, undriven, system monologue, and I bury the lead. Paul accused me of doing that once. I never forgot that line, burying the lead. What I want to talk about is conversations with the system or monologues where the system's just talking to me. So right now we're just talking about the system talking to us. Turns out you can write that in signal space. There it is. I changed these into phi's via students, Graham Schmidt. And I project these things onto basis functions. So Rn is the output R over in some interval projected onto these basis functions. We do all of this business. And this, maybe people knew this before. I've never seen it presented this way, but look what you get. If you reject that output, X, onto this set of basis functions, you get this R. There's the initial state of the system. And there's some noise that was added to the input that we had before. Okay, that's a colored noise channel. Now, you got to be careful here. The
So is
analogy
the X0 a Gaussian?
might be
Or is
both.
W,
It might. It's coming in.
W is just a receiver noise? What is W?
So there. So I'm going to assume that's white dash. Okay? All right? And what I, again, buried another part of the lead is what I'm going to be interested in here is what was the initial state of the system. And this system, I want to make sure it's completely observable, completely controllable, all of that.
So just a quick one.
Yes, sure.
Bottom line, R of t. R is just a number. It's the position of this thing as a function of time. And W is just a number. W is
Stochastic.
But it looks to me like C is a matrix and X is a vector.
Yes.
So how does, pardon my ignorance, how does a matrix times a vector give you a scalar?
This is a row vector.
Oh!
That's it.
Thank you,
And
thank you.
this is, again,
Thank
this
you.
is, it's just a matter of disciplinary divides, which I'm going to jump to, talk a little bit more about that later, because we're going to jump a big one. But thanks. There, we do all of that, we end up with this colored noise channel. Okay? Now, what I don't want to do is push this analogy too far. It's not that, it's of the form, okay? But usually we don't think of the device trying to tell us something about itself, okay? Trying to tell us its state. But that's what the equations say. It's in that structure. So what you could do is, if you can ask the question, how much can I know about the initial state of that system? I can begin to think about it in terms of mutual information and specify it in bits. Okay? And that's the idea. Now mind you, I'm not saying that this is what happens, but what we're doing as information theorists, communication theorists, is applying bounds. So I can tell you what the maximum rate of information flow between that state and my observable is by looking at this equation. And that's just colored ones. Wait, it gets better. And this one I really like. It's kind of poetic. Bust this up into individual state variables. It's a multiple access channel. Right? The columns are Q. Multiplied by each one of those state variables, it's a multiple access channel. Okay? And this is something Roy and I worked to death on in kind of this form. By looking at this Q, you can begin to think, well, some states are created more equal than others. Some states can tell us more about themselves than other states can. And it's just a different way of looking at how you measure a system. Usually it's done in terms of estimation. Here, there's a communications context for it. So this was kind of interesting to me. Finally, it gets even better than that. I can talk about energy constraints exactly this way. Just the way we talk about them in communication systems. Z is just some positive definite matrix that we stick in the middle there to make things right. Okay, I say less than or equal to some energy budget because maybe the system's dissipated. I haven't said whether it is or isn't. If it's not dissipated, it's equal. And the coolest thing is that if we can, we can take this thing down, 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 down in size scale, and we can begin to think about discrete things, where stuff can be, energy levels it can occupy. And if there's a discrete set of these x zeros, you can begin to think about it as a digital detection problem. Okay? So again, this may be, this may be old news, but I haven't heard it before. And it could be because my ears have been closed, but I haven't heard of this before. All right, that's an example. It's not worth bothering with. All right. Now, where it gets, I think, even more interesting is when we start talking about the dialogue. So now, usually the estimation problem is, so if I want to know what Harris is thinking, I watch it. I watch it. But I watch it. He's twitching. Again, he looks pretty calm right now. But he does have the look, meaning he will be graduating soon or somebody will die.
That's true.
So you got that.
You got the full information.
But now, I can also talk to Harris, right? So I can interact with them. So now the question is there something that I can do to figure out that state by probing, doing probes? So let's set it up. We do exactly the same sort of signal space workup. I just did the math to make it so that you believe me. I haven't published it anywhere. Blah, 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 blah. The punchline is this kind of, it's not complex looking, it's just busy. Sorry about that. I should have just consolidated things. But basically, you've got a sequence of measurements that you make over different epochs. Discrete again. Remember, we're talking about things that are continuous waveform, but we're doing the communications theory thing. We're projecting them onto a basis, so we end up with a discrete set of numbers. That's our observation. This is how it's related to x0. And that's how it's related to the input. And I did something with the input. Peter would appreciate that as bang bang control. Basically, I'm making sure the way I apply control to this system is I apply impulses as opposed to any sort of continuous waveform. Completely general, because all I got to do is bring the delta for when I apply these impulses down to 0, and life is exactly the same. So again, here's my observation. There's the thing I care about. There's the dependence on my probes. There's the noise, which now varies as a function of interval. And we can now think about designing iterative probe sequences. Okay. Now, maybe you were hoping I was going to show you one of these iterative probe sequences. No, I'm going to show you the basic. We'll assume that we don't touch the system at time equals 0. And then what we're going to do is we're going to design F1 to maximize, say, one of the things you could do would be to maximize the initial information between X and R. Okay? Given that you saw R and the rest of this. So iterative probing sequences. I haven't seen, now mind you, communications theorists, we do iterative stuff just like this all the time, right, in our detection problems. I haven't seen it applied to systems. So,
Are you disturbing the state of the system when you're...
oh, hell yes. Oh, yes. Oh, most definitely. Okay, and that's the difference. Estimation is very passive. I don't like this.
It depends on the scale. I guess for the MIMO channel, you're not really...
Oh, here.
The energy levels are so...
Okay, careful. That's, I should issue that disclaimer. These are essentially disjoint snapshots. So I'm not suggesting necessarily that this should be applied to MIMO channels. I'm just looking at it as watching that click-clack go back and forth on my desk. What can I say about its future? What can I say about its initial state? I see it going click, 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 click. Now what was it doing 10 minutes ago? I'm making up a problem. Okay?
So I've got these masses on the table, the diagram you showed us. We don't know what the initial condition was. That's what we're trying to find out.
Yes, 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 yes.
And what we're going to do is we're going to smack it in various ways in our attempt
Smack
to
and
find
watch, smack and watch, smack and watch.
out, in our attempt to find out what was that initial condition. Is that the problem we're trying to solve?
Thank you. Perfect. Paul, I love you. Love you for 25 years. Oh my God, I don't want to say how long. Oh, this is terrible.
It's about 25.
No. It's a lot longer than that.
Oh, right.
Oh, man. Isn't that what Paul just said? Here's the system. Here's the thing that's asking the questions of the system. It shouldn't be watching X, that's screwed up. That should be R. There should be a summation in there with some noise, but that's what Paul said. Now here's the interesting thing to me. How many of you know a little bit, just the tiniest bit about chaotic systems? So Jerry, correct me if I'm wrong. The fundamental thing about chaotic systems is that if I started out in this state, and I wait some time, and then I started out in this state plus epsilon, and I wait some time, those initial conditions produce divergent trajectories of the system. Now, here's a question. What I did was I put a feedback loop in here, right? Well, here's a question that I'd love to answer. Maybe somebody already knows, but again, nobody's told me. What if the optimum querier makes the system unstable so that you can distinguish different initial conditions more easily? And that's the extent, there I've got to cut off because I can think of a variety of reasons why that might not be the case, mathematical reasons and intuition reasons, but it seems
But
like
the
an interesting thing.
optimality is in the sense of when you're all done, you want to go back and learn the initial position.
Yeah, that has refined the information about that has reduced the entropy. Another way you could, the entropy reduction. It has reduced the entropy of the initial distribution of X maximally. And by the way, you mentioned this, but we didn't elaborate. That initial distribution, depending on how I pick my states variables, that's a very physical sort of quantity. Look at against Boltzmann distribution. Right? Energy. Everything's based on energy. Okay? All right. All right, we'll... Right. Yes?
So what is the present state of art in trying to get the initial conditions in this kind of
State observers. I'm sorry, and I didn't mean to say sound glib. State observer, you can use Kalman filters, you have a model of the plant, you watch what's going on there, you do innovations, but you don't touch the system. That's the difference here. You don't touch the system, you watch the system. Here, you're touching the system. And it's specifically the notion that you want to figure out where it was before.
So that's why you call it dialogue?
Yes, no, there's no, I'm sorry, yes, that's why I'm calling it a dialogue. So we move from monologue to dialogue. Most of the stuff that I'm familiar with is monologue, This is a dialogue, and it's a communication problem.
So, by touching the system, aren't you getting some more, you're going to disturbing the system so that you don't get the...
Okay, well, what you did, and I think what you're saying, you're doing an intuition. Let's go back to this picture. And that's true and real. But look at the way this thing is set up. What you're saying is that maybe there's some noise sitting on that F. Okay? Well, same difference. Okay? So now the question becomes, if there's a certain level of noise sitting on the system, should you do something, or should you shut the hell up and leave the system alone? Okay, so there's a continuum. Right? Everybody? So I'm going to quick blaze through biology, because I want to show you this thing that is the most interesting to me, the most mysterious, about which I know least. This I know a little bit about. I'm going back to my roots. Here's the fly. Fly starts out as a blastoderm, bunch of cells. I don't know how many, 1,000, maybe less. And it differentiates. I don't know the timestamps on these things, and you end up with something that looks like a lot like a fly, segmented, does all that good stuff. All right. Nobel Prize in Medicine, 1995. Christine Nussling-Ballard. She posited morphogenes. Okay? And morphogenes are genes that control development. And she did this at a time when you could do genetic studies, gene expression studies, knockout gene studies, where you could take out particular genes. They got really cool names like hedgehog and what's another one? Hunchback, wingless, all these cool genes that you can pull out. And you watch what happens to the development of life. And what they found, and the basic supposition was that different signal concentrations, a cell is a little engine to manufacture proteins. So it's pumping out proteins. It also listens. It has receptors on the surface. And on the inside, things diffuse through the, or are transported through the membrane. And the idea is that different signal concentrations can do something with gene expression. So a cell is sitting there, if it gets a particular signal, it will do something different. Okay? The egg imposes an initial gradient. Okay? I don't know whether that's actually been measured, but yes.
I've heard, in connection with this,
Yeah.
that the site of fertilization, where the sperm hits the egg, creates
Polarization? It might. I don't
It gives
know.
it a certain differences between here and there, and that sort of sets the way things have developed.
Well, certainly there's differences. Maybe that's exactly what it is. I know that it was in the 20s. It was E. Just, actually, at Dartmouth. Yeah. There's a variety of reasons I should know that. Talked about mechanisms for when a sperm fertilizes an egg cell and the cascade of things that happen. So that's perfectly reasonable. They, however, talk about already implanted in the egg variations. Whether that's true or not, I'm not sure. But the structure is this. You have some initial signaling gradients. However they're set up, there's extracellular diffusion. Okay? So what that means is that the molecules, you pump them out, but just like, I just communicated with you. So whatever was in my mouth, it's going to get to you. Okay? Hopefully I'm healthy. So extracellular diffusion, that's a bad example because there's convection and all this other crap. That's actually useful. Neighbor interactions. The developing cells do their own thing. You end up with embryogenesis. You end up with a fully formed thing. What I want you to think about here are a few things that bother people like us. First off, to my knowledge, nobody's actually gone in and measured these gradients, which makes sense. It's kind of hard. These are really teensy sort of things. We're talking about microliter, more than microliter volumes, less than microliter volumes. A few molecules, what are you actually measuring? So really the only way you can do this is with recombinant or knockout gene studies. So nothing hasn't actually been measured, to my knowledge. What I was saying there, simple diffusion can be disrupted in a variety of different ways. I don't know whether people have done disruption studies. I've asked around, haven't gotten straight answers. So I don't know, about this diffusion thing. Here's another thing that has been given a lot of press in the literature. If you look at a diffusion profile, it can vary very gradually. But when you see these divisions between parts of this animal, there are sharp divisions. So the question becomes, does the cell trigger at a particular point? Does it trigger randomly? What is actually going on? How does it actually interpret these gradients, if these are indeed gradients that it's using? And that bugs me. Because we all know, sitting on the knife edge of something, designing something based on absolutes and knife edge decisions on something that is shallowly varying, okay? It seems like a bad engineering move. So that makes me nervous. The other thing, so now you're going to do some analysis, right? Well, these cells, they're a fungus that have as many genes as we do. Okay? So these things are complex, they're very complex structures. And trying to model them and all the possible things that they could do could drive you completely nuts. I don't want to go nuts, so I kind of ignore it. It's a potential modeling morass. So what I decided to do is look at it. And here's the interesting thing. Most of the time, almost all the time, development proceeds along a particular path and poof, something pops out. It's reliable. Okay? As soon as you say reliable, the communication theorist in you says, shiny. Because there's some sort of communications theory thing going on here. Okay? Well, what can I do to talk about this reliability? The other thing that makes it important is that cell fix is not a gazillion different types of cells. They've mapped out. It's very clear what cells become and how they become what they become. I shouldn't say how. The sequence of what cells do as they develop. So that's very clear. And it's amazingly reproducible. So we have digital in some sense, and then we have amazingly reproducible on the other hand. So here's the question that I've asked. Can I at least use some information theory, communications theory, to get my hands around what is a possibility with these sorts of systems? Is it possible for a gradient to convey the information that it needs to convey? Is it, or do I need some other mechanism? That's good for biologists, because if you show physically this can't happen, then there's got to be another mechanism. So that's where I'm coming from. And having done some of this biological work, it is really easy to get bogged in. So you do need some sort of overarching principle that can help guide things. Okay, so I'm going to really blast through this, and I don't think it's really worth digging into too much, other than saying something about the communications problem. What I did on those other two slides was just show you something about the channel. Okay, and it turns out the fusion channels suck. Okay, for long distances. Very long is 100 microns. Okay? Cells are on the order of tens of microns, individual cells. So 100 microns away, diffusion sucks in two ways. The signal intensity goes way down, the concentration intensity is not that controllable, and if you try to vary the concentration really fast, right, like you would in a communication system, use frequency. You're screwed there too, because both of these things go down doubly exponentially. Yes?
Shouldn't it be said that context is everything here, because every cell has DNA to do anything that any of the cells can do.
In that last term, yes.
And it's the context that's set by somehow the chemistry of the cell that expresses this and not that.
Well,
and it's that context that's being communicated.
And that's, I agree completely. Maybe I'm saying it wrong, or maybe I'm misunderstanding what you're saying. But yes, those cells are talking to each other, and there's this external context. And my question is, they say it's diffusion. I don't really believe them. Okay, but maybe it is. And the way I could believe them, and let me just skip to the last slide here, because I'm showing you a bunch of stuff. This will only the information theorists will appreciate this. How many know Sergio Verdu's paper, Bits Through Qs? Okay, great. This is the version of Bits Through Qs. It's parallel bits through Qs with reordered outputs, which drives you crazy. I showed this because I couldn't not show it, because for the past 6 months I've been beating my head against this problem. And that probably shows something about the softness of my head. The point is, there's a bunch of stuff that you can say, and you can begin to start. Here's the killer, nice thing. You can begin to talk about bounds for a variety. See, biologists go crazy. They say, oh, you shouldn't use this model for diffusion. You should use that model or the other model. Information theory is really good at talking about worst-case distributions, and that's what we were able to do in the end of Chen, who is now in China controlling the power. But here's what I want to tell you. I don't know where this is going yet. Okay, NSF, we tricked NSF into funding us. Hopefully I won't go to jail for malfeasance. But we know that development has a schedule. We know that cells can have finite types, so there's that digital portion. You can do experiments. This is the way experiments are usually done. You start growing the flies, you stop them growing, and that's euphemism. At day 1 or hour 1, do an assay, see what they're doing. Day 2, day 3, various places in between to figure out what they're doing. And what you could do is you could figure out what particular cells are doing when, and how much information in the abstract they need to figure out what it is that they need to do. So it's a little bit of a fishing expedition, perhaps, but it could be backed by experimental studies. Metabolism is well understood and easily measured because you know how much energy it takes to make the various proteins. You know mostly what a cell is doing. So there are things that you can do there to get a handle on the energy. And the sort of questions that you'd ask are this. Can morphogens, these signaling agents that nobody actually has seen in vivo, but you imply they're there because you knock out the gene that produces them, can they really convey the info in time? Reliably? And, this is the other cool sort of thing, and a way a teaser for this sort of work in this talk is, what if I could take a seed, throw it in the ground, and grow a house? Literally. Well, that's the kind of stuff that we like to worry about, right? Not growing houses, but what is the space of allowable structures? We're talking about a communication system, talking about anything, that's what we do for a living. So that's where I'm going. Yes, sir.
Are we talking about communication between a cell and another neighboring cell or within the cell?
Any and all. Turns out, if you look inside a cell, that there are receptors in there too. And some signals diffuse right through the cell and go directly to the receptor. Some are bridged by the outside of the cell and transported in. Some are actually sensed at the outside of the cell and never let in. So any and all. So this is a scale-free sort of thing. But right now, I'm talking about cells.
When you mentioned sharp changes in diffusion gradient, you were talking about the cell boundaries.
I'm talking about a bunch of cells. Okay, here's the head. Remember that picture of the blastoderm? There's the head. There's the tail. How's the tail know it's a tail? Now, wait, how does that cell know that it's going to be a rib or a particular portion of the neural tube? Okay. Yes. I don't want to snow anybody because this is I barely know what I'm talking about. All right. So the idea is my objective here is balance on what is and what is not possible, and made some progress on the diffusion problem, which is a ubiquitous form of communication between cells. But just as you say, there's mechanostimulus. I actually did my thesis in mechanostimulus, auditory physiology. There's a zillion different things you could use. And people were like, in 3 years, I'm not going to consider all of them. All right. I think I can do this in 5 minutes, because this is what I know least about, but I feel like instructions. All right, this is my buddy Jim. He's a string theorist. He called himself a super-symmetry theorist, but he's a string theorist. He's a chair professor down at UMD. Has various educational materials, fantastic teacher, which is probably why I was able to learn a little bit that I was able to learn about this. To me, supersymmetry, a lot of physics has been inaccessible. High energy physics, completely inaccessible to folks like me. And that may just be me, that thing that it is folks like me. So what Jim has done is, what he's been able to show is that there are these structures that perhaps, if supersymmetry is right, that you can use to define any possible universe, including ours. Now, there's a lot of work that needs to be done there's lots of I's to dot, lots of T's to cross, but this structure that he's discovered it just has, when you kick the wheels of it, it's like, hey, that makes sense. It correlates with a bunch of different things. So, you see I'm using very non-descriptive sort of language, because I have to. I can't tell you exactly. But here's the quick overview of particle physics. So here's the cool thing that I knew but I didn't really know, and it only really hit me in the past few years. Well, actually, about 5 years ago, Jerry sent me a paper and said, hey, you should learn about quantum computing. And there was a primer that talked about quantum computing. Turns out that physicists view the world very much the way communications theorists view the world. Fundamental particles are eigenfunctions for some system. That system is amazing. Well, I'll tell you later about the system. But they're eigenfunctions of a system. And the most famous is Schrodinger. I say Schrodinger-esque because there's a variety of different systems that could be Schrodinger-like. Depends upon how you impose your potential and energy constraints. These fundamental particles break into two sets according to supersymmetry. I think according to supersymmetry. Certainly according to supersymmetry, but maybe that's just a general sort of thing. Bosons and fermions. Fermions are things like electrons. Bosons and protons, correctly, Paul?
Photons.
Photons have half spin, so they're fermions. Well, I don't know what the hell I'm talking about.
Photons have spin 1, so they're both.
Oh no, the bosons, right? Okay, so integer spin is a boson, and spin is, see, spin is, oh my god, what is it spinning around there? to mode, the equation, which means spin or charm or color. Heard about colored quarks? All right. Blah, 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 blah. Here's the thing that Jim discovered, that you can look at these operators that operate on the individual eigenfunctions. So, when we think about eigenfunctions, you can turn one thing into another via various operations, translations, or rotations. Well, there are these systems of operators in the particles, and he calls them, there's a relationship between them, and he puts them in a graphical form called an adinker. What's cool about this? All the equations and all the operators, this floored me, I didn't know this before. Everything's linear. Okay? And electrical engineers, I tell my students this. One of the things we always do is, if it's not linear, we run screaming. We want to linearize it right away. Everything's already linear. Okay? So that's a great thing. His adinkers faithfully represent all possible realities. Okay? And this is the thing that kind of just blew me away. If you look at these structures, they can fold, but not all of them can fold. Okay? It's not like it's everybody can fold up. These graphs, they can fold in upon themselves and create other adinkers, but only under specific rules. And that's the punchline that I want to get to quick. All right. So in any case, the reward for me is that this is a bridge for me to get into supersymmetry. I probably will not understand it the way Jim does and his cohort, but I can certainly understand these graphical structures and their interrelationships. And if they represent a physical reality, I'm happy as a clam. There's the other thing that I'm kind of hinting at. Even though the math is very similar, this is a disciplinary gorge, which I find just even in notation. So, watch out. Okay. What's a basic adinker construction? You got nodes, you got links. These are the particles. These are the operators. There's this thing called dashing, which flips so that you end up, you don't violate the exclusion principle. Details, details, details. Many possible graphs.
Question.
Sir?
What are the nodes at the edges on the graph?
Sure. The nodes are the solutions to these sets of equations. So a node is a particle, like a proton, like a unseen selectron, antiproton, whatever. Okay? The links are operators that mathematically map those wave functions. I didn't say the wave function, I should have said the wave function. Those nodes are particles. The particles are described by wave functions, and those wave functions are interrelated via linear operators. Okay, so the graph represents a photon, for example, might map into a photon, boson maps into something with a half spin, fermion, which again, with another operator can map again into a boson. So, I'm almost above, I'm really above my head. And I'm relying on the graph structure. So the little bit that I understand, I was able to learn through looking at the graph structure. Nodes are particles. Links are operators that map one particle to another, mathematically, the wave function. All right, here's the construction. N cubed. Color. Okay. Bosons do not map to bosons. Bosons map to fermions. Fermions map to bosons. Bosons are white. Fermions are black. You start out with a cube. Label a point of boson. The cube is suddenly labeled. Okay. See that? You pick one point. It's got to be labeled alternately. There it is. Then you start coloring it. You color according to direction. That's the operator. The operator is the direction. So here, all those in that direction are red. All those in that direction are green. That last thing that I talked about, called the exclusion principle, let's look at this guy. Better yet, let's look at this guy and this guy, two bosons. They share these two fermions. Unfortunately, the operator set that maps this boson into these two fermions is exactly the same as this one. Can't happen. Unallowed. That's what physicists tell me. I believe it. Okay? So what you do is you invert the sign, so we do a dashing, and we end up with a valid adinker. That's where you start. In this N cube, labeled N cube. Once again, this is a form of a potential reality.
So before this exclusion is saying that two particles cannot be in the
Two
same place
bosons.
at the same time, in general.
What they're saying is that the operations, the same place at the same time, they can't occupy the same energy space or state or something. What was explained to me is that this maps into, there's a set of operators that relate the wave functions.
Well, no,
An equivalence, you're asking me to actually interpret it, and I'm above my head.
Yeah, well, what I was trying to say is that I don't see the space. Where is space that this is a...
These are operators. They're operators, okay? So the operators are spatial derivatives or time derivatives or whatever sort of derivative, or whatever sort of linear operator. You're asking me to relate this to actual physics, the physics that we know and love, like Pauli exclusion? I can't. Okay, so that's just my ignorance right now. Okay? But the point is this, that represents a reality. So if you bear with me. There's a bunch of, now once you got that structure, you can twist it and turn it in a bunch of different ways. How, I'll call it engineering dimension. Ask me to describe engineering dimension. I can, but I can't. Because I don't really. But the point is, there's a bunch of different conformations that you can turn these things into, where you keep things on the same level. So fermions are on the same level, bosons are on the same level, and you can arrange them in such a ways. All of them correspond to a Feynman-like self-consistent particle operator system. So they obey the laws of physics, is what that's saying. That's important, because what that says is that these things are exact representations. You can, if you look at the Adinkra graph, you can actually generate a set of self-consistent equations. That's pretty amazing to me. And it's pretty amazing to Jim, because he's, you know. So let me finish. Here's a cool thing. Some Adinkras can be folded, collapsed. How many of you have heard about holographic universes? Well, you can think of a collapse as a projection operation. So let's look at this high-level Adinkra. You undash it first. You label the nodes according to an algorithm, which is easy, but I won't describe it. And the point is, I can go from this higher level Adinkra. This one has 8 nodes in it. No, 16 nodes. Yeah, 16 nodes in it. And I can label it appropriately, this one, and it collapses into the one that I had before. What you have to do is you have to ignore these dashes because we did some undashing. Right? You can't do that all the time, though. I don't have the link to the video. Here's what got my juices flowing. Because I was listening to this. Yeah, Jim, yeah, that's great. Oh, I'm glad you're really happy. Yeah, you're doing the best physics of your life. You know, it's great. Well, it turns out that the only Adinkras that can be folded, so we have this algorithm for labeling the nodes. The only Adinkras that can be folded is if this set of mathematical relationships that we know and love as communications theorists can be applied. So LBC, red track. Any of block code. You taught the code for some days.
I've never seen that.
You've not never seen this, but you certainly
I've
seen
never
LBC.
seen LBC used.
This way.
Yeah, I've never seen.
So you got an LBC, you've got a generator matrix, right? Column 1s and 0s. Okay? That generator matrix elaborates a set of code words. You add those columns together, modulo 2, and you have a set of code words. That's this. That's C. If you can take those code words C and combine them with the addresses of all of those nodes and end up with all the addresses of the nodes and no others, you can fold it. Careful, careful, careful. Not just any linear block code, but a double error correcting block code. Okay, so here's the picture that I want you to have that immediately formed in my mind, and we don't know whether it's an artifact or anything else. But you have some high dimensional Adinkra, something that has a bunch of different operators in some higher dimensional space, or just a bunch of different operators. Leave it at that. I don't want to do the spatial analogy just yet. That thing, there may be Adinkras up there, and there are, that when you project them in the right way, in a lower dimension, you get another set of particles. You project them in the right way, you get another set of particles. So you end up with this kind of nesting operation that's controlled by, it's not just a code, it's an error correcting code. So that makes me interested. I don't know how interested yet, because I don't know, as you see, I don't know enough about it, about the physics to really understand. But I think the mathematics is close enough that we can
When you
play
say
with it.
double error, you mean like 2 bits in error? Or?
Yeah, so like this, that's a trivial double error correcting code. I either send 11111 or 0000. Right? Any 2 errors can be corrected. And 1 error, you know. In any case, it's this mathematical artifact, or here's the thing again. Think of it that you are designing a universe, okay? And you want to make sure that it's all self-consistent. Are there some perturbations that happen in your universes that you want to preserve something as you do the projections on them? Now, again, I'm waving my hands. I don't know what I'm talking about here. But, you know, that's the question that immediately pops to mind. If you're designing a universe, do you code it? Or why is it coded? So, you know, what I want to say, I'm done. And the thing that I want to
Why
impress...
only 2 errors?
Pardon?
Why only 2 errors?
it could be, I thought a little bit about it. I don't know why, but I look at this and, you know, you're doing it on a hypercube. And then you saw that kind of Pauli exclusion sort of thing where, you know, two edges can share, you know, two. I'm just not, it may have something to do with the structure of the way he set things up. It may have nothing to do with any other perturbations. I haven't talked about anything stochastic here, by the way. There's nothing stochastic here. It's a structural relationship. Okay? So, I answer the questions to the best of my ability. Meaning I don't know, but I don't know whether it's real or not. But it excites me to look at it. So I guess the point here is that, you know, physics, you know, they're superheroes. But I think that as communications theorists, we may be selling ourselves short. We've done a great job with things in the practical sort of sense. We've built the information age. But it might behoove us, since we have the mathematical tools and we have a different way of looking at things. I pointed things out to Jim. He said, oh, that's interesting. I hadn't thought of it that way. Which is, you know, string theorist. I'm like, wow, very good about that. Then again, he's a very good teacher and very nice, so he may be. Why is he bothering with this? But in any case, I think if you combine the two, you can get something even better. We can be the new Sputnik children and conquer the world. So that's it. The punchline of all of this is that I think communications theory, I'm trying to convince you of, maybe even get you interested in, communications theory can be applied to things that we normally don't think of applying them to. The two most interesting things to me are the biological question and this idea of observing systems. Those are things that are most accessible to me. The previous thing on the dangerous could be a really interesting sideline, or, you know, it could be 10 years from now, I could open up the paper in October and see Jim's thing. All right, thank you guys.